Welcome. In this session, we'll tackle problem number 1134, Armstrong number. This problem explores an interesting mathematical property of numbers, where the sum of its digits raised to the power of their count equals the number itself. Let's dive in and uncover the approach to solving it. An Armstrong number, also called a narcissistic number, is a number that equals the sum of its own digits, where each digit is raised to the power of the total number of digits in the number. For instance, the task here is to determine if a given integer n is an Armstrong number. If it is, we return true, otherwise, we return false. Let's look at an example to clarify. For the input n equals 153, we first note that this number has 3 digits. The goal is to compute the sum of each digit raised to the power of 3, and check if this sum matches the original number. Breaking it down, we calculate the individual contributions of each digit of 153 raised to the power of 3. The first digit is 1, so 1 raised to the power of 3 equals 1. The second digit is 5, and 5 raised to the power of 3 gives 125. Finally, the third digit is 3, and 3 raised to the power of 3 results in 27. Adding these values together gives us 1 plus 125 plus 27, which equals 153. Since this sum matches the original number, 153 is indeed an Armstrong number. Now, let's consider another example, n equals 9474. Here, the number has 4 digits, so each digit will be raised to the power of 4. For 9474, we start with the first digit, 9. Raising 9 to the power of 4 gives 6561. The second digit is 4, and 4 raised to the power of 4 equals 256. The third digit is 7, which when raised to the power of 4 results in 2401. Finally, the fourth digit is again 4, and raising it to the power of 4 gives another 256. Adding these values together, 6561, 256, 2401, and 256, we get a total of 9474. Since the sum equals the original number, 9474 is also an Armstrong number. On the other hand, let's consider a case where the input number is n equals 123, which has 3 digits. For 123, we calculate the sum of each digit raised to the power of 3. The first digit, 1, raised to the power of 3 equals 1. The second digit, 2, raised to the power of 3 equals 8. The third digit, 3, raised to the power of 3 equals 27. Adding these values together gives 1 plus 8 plus 27, which equals 36. Since the sum, 36, does not equal the original number, 123 is not an Armstrong number. To summarize, the problem includes constraints such as ensuring the input is a non-negative integer between 1 and 10. Note that single-digit numbers are always Armstrong numbers, and the solution must handle edge cases and the upper bound efficiently. To solve the Armstrong number problem, we first need to understand its definition. An Armstrong number is a number that equals the sum of its digits, each raised to the power of the total number of digits in the number. For instance, the number 153 qualifies as an Armstrong number because if we take its digits, 1, 5, and 3, and compute 1 cubed, 5 cubed, and 3 cubed, the sum equals 153. With this in mind, one approach we considered is the brute force method. The intuition behind this approach is to directly calculate the sum of each digit raised to the power of the number of digits, then compare the result to the original number. The steps involve converting the number to a string to extract its digits, determining the number of digits, iterating over each digit to compute its power, and finally summing these values. While this approach is simple and easy to implement, it has inefficiencies, especially for large numbers, due to repeated conversions and power computations. Its time complexity is proportional to the number of digits, O(d), and its space complexity is also O(d). While straightforward, its inefficiencies make it less ideal for scalability. In contrast, the optimized approach builds on the brute force method but eliminates redundant computations to improve efficiency. Instead of converting the number to a string, we use integer arithmetic to extract digits directly. Additionally, we calculate the number of digits using logarithms, specifically log base 10, which avoids string manipulations. By doing this, we can directly compute the sum of each digit raised to the power of the total number of digits without storing intermediate results. This optimization maintains the same time complexity, O(d), as we still process each digit individually, but its space complexity is reduced to O(1), as no extra storage is required. This makes it more efficient overall. While slightly more complex to implement because of the use of integer arithmetic, this approach avoids unnecessary operations and is particularly suited for scenarios where efficiency is a priority. Another approach we considered is the pre-computation method. The idea here is to generate all Armstrong numbers within a specific range beforehand and store them for quick lookups during queries. To implement this, we pre-compute Armstrong numbers for a range like 1, 10 to the power of k, offline, then check if the input number exists in this pre-computed set. This results in an extremely fast lookup time of O(1), but the pre-processing step is computationally expensive, with a time complexity of k*10 to the power of k, where k represents the average number of digits. Additionally, the space complexity is significant, as we need storage proportional to the number of pre-computed Armstrong numbers. While this method is ideal for scenarios with repeated queries within a fixed range, it becomes impractical for larger ranges due to the high pre-processing and memory overhead. Therefore, it is best suited for specialized use cases where these trade-offs are acceptable. After evaluating these approaches, we chose the optimized approach as our strategy. This decision was based on its balance of simplicity and efficiency. The brute force method, while straightforward, suffers from redundant operations and inefficiencies, particularly for larger numbers. On the other hand, the pre-computation approach is highly efficient for repeated queries but comes with significant pre-processing and storage requirements, making it less practical for general use cases. The optimized approach stands out because it simplifies the problem by leveraging mathematical observations. For example, we can determine the number of digits using logarithms, reducing the need for conversions, and integer arithmetic eliminates intermediate storage, which improves space efficiency. While slightly more complex to implement than the brute force method, it is highly efficient for single queries and scales well for typical problem constraints. Overall, this approach achieves an ideal balance of efficiency, simplicity, and scalability, making it the most suitable choice for this problem. To determine if a number is an Armstrong number, we need a clear step-by-step approach. First, we take the input number, which we'll call n. It's important to note that Armstrong numbers are defined for non-negative integers, so if the number is negative, we can immediately return false. Next, we convert the number into its string representation. This makes it easier to access each digit individually without complex arithmetic. For instance, the number 153 becomes the string 153. Once we have the string form, we calculate its length to determine the total number of digits, which we'll call d. For example, if the input is 153, the length of the string 153 is 3, so d equals 3. These initial steps lay the groundwork for the calculations that follow. Now, we calculate the Armstrong sum, which is the crux of the algorithm. We start by initializing a variable, Armstrong_sum, to 0. This will store the cumulative sum of each digit raised to the power of d. Then, we iterate through each digit in the string representation of the number. For each digit, we convert it back to an integer, raise it to the power of d, and add the result to Armstrong_sum. For example, with n equals 153, the digits are 1, 5, and 3. We calculate 1*3 equals 1, 5*3 equals 125, and 3*3 equals 27, and add these values together to get Armstrong_sum equals 153. Finally, we compare this sum to the original number, n. If they are equal, the number is an Armstrong number, otherwise, it is not. The result is then returned as true or false accordingly. There are several key insights to understand about this algorithm. First, the uniqueness of Armstrong numbers comes from raising each digit to the power of the total number of digits. This property ensures that only specific numbers qualify as Armstrong numbers. Second, the most computationally intensive part of the algorithm is the power operation, but Python's *** operator handles this efficiently. Third, converting the number to a string simplifies digit extraction, eliminating the need for repeated division and modulo operations. It's also important to consider edge cases. For instance, single-digit numbers are always Armstrong numbers because any number raised to the power of 1 is itself. Negative numbers are excluded by definition. Lastly, while Python can handle large integers without overflow, this might be a concern in other languages with fixed integer sizes, so it's worth keeping in mind when implementing the algorithm elsewhere. Let's walk through an example to see the algorithm in action. Consider the input number 9474. First, we convert it to a string, resulting in 9474. The length of this string is 4, so d equals 4. Next, we initialize Armstrong_sum to 0. Now, we process each digit. For the first digit, 9, we calculate 9 (4 equals 6561 and add it to Armstrong_sum, making Armstrong_sum equals 6561. For the second digit, 4, we compute 4 (4 equals 256 and add it, resulting in Armstrong_sum equals 6817. For the third digit, 7, we calculate 7 (4 equals 2401 and add it, giving Armstrong_sum equals 9218. Finally, for the last digit, 4, we compute 4 (4 equals 256 and add it, yielding Armstrong_sum equals 9474. At this point, we compare Armstrong_sum to the original number, 9474. Since they are equal, we conclude that 9474 is an Armstrong number, and the algorithm would return true. Finally, let's analyze the complexity of this algorithm. The time complexity is O(d), where d is the number of digits in the input number. This is because we iterate through each digit exactly once and perform constant time operations, like conversion and exponentiation, for each. The space complexity is also O(d), as we store the string representation of the number, which has a length equal to the number of digits. These efficiencies make the algorithm well-suited for most practical use cases, especially when implemented in Python, which handles large integers and power operations efficiently. This Python implementation solves LeetCode problem number 1134, Armstrong number. The function isArmstrong determines if the input number n is an Armstrong number. Here's how the solution works. First, the number is converted to a string using str_n. This allows easy access to each digit of the number. The length of the string is calculated using len, digits, which gives the total number of digits in the number. This value is stored in the variable power. Next, the sum of each digit raised to the power of the total number of digits is computed. This step uses a generator expression inside the sum function, sum int digit power for digit in digits. The generator iterates through each digit, converts it to an integer, raises it to the power, and accumulates the results. Finally, the computed sum Armstrong_sum is compared to the original number n. If they are equal, the function returns true, indicating that the number is an Armstrong number. Otherwise, it returns false. This function handles edge cases implicitly, such as single-digit numbers. A single-digit number is always an Armstrong number because any number raised to the power of 1 is itself. The implementation is efficient and concise, leveraging Python's powerful string manipulation and mathematical operations to solve the problem directly. This is the Java implementation of the Armstrong number problem, LeetCode number 1134. The logic mirrors the Python implementation, converting the number to a string to extract digits, calculating the number of digits, and computing the sum of each digit raised to the power of the total digit count. Java-specific differences include type declarations, the use of integer to string for conversion, and math.pow for exponentiation. The method returns a Boolean indicating whether the input number is an Armstrong number. To determine if the number 153 is an Armstrong number, we begin by converting the number into a string so we can easily access each of its digits. Here, n is 153, and converting it gives us digits equals 153. Next, we calculate the total number of digits in the number, which is simply the length of this string. Since there are 3 digits, power is equal to 3. Now, we compute the sum of each digit raised to this power. Using a generator expression, we calculate the first digit, 1, raised to the power of 3 is 1 3 equals 1, the second digit, 5, raised to the power of 3 is 5 3 equals 125, and the third digit, 3, raised to the power of 3 is 3 3 equals 27. Adding these results together gives us Armstrong_sum equals 1 plus 125 plus 27, which equals 153. Finally, we check if this computed sum matches the original number. Since Armstrong_sum equals n, or 153 equals 153, the result is true. 153 is indeed an Armstrong number. The final output for this example is true, confirming that 153 is an Armstrong number. Now, let's consider another example with n equals 9474. First, we convert the number to a string to extract its individual digits. Here, digits equals 9474. Then, we calculate the number of digits, which is the length of this string, so power equals 4. To compute the sum of each digit raised to the power of 4, we again use a generator expression. For the first digit, 9, we calculate 9 4 equals 6561. For the second digit, 4, it's 4 4 equals 256. For the third digit, 7, we get 7 4 equals 2401. Finally, for the fourth digit, 4, we calculate 4 4 equals 256. Adding these results gives us Armstrong_sum equals 6561 plus 256 plus 2401 plus 256, which equals 9474. Now that we have the computed sum, we check if it equals the original number. Here, Armstrong_sum equals n translates to 9474 equals 9474, which is true. This confirms that 9474 is also an Armstrong number. For the final output, we return true. Moving on to another example, let's take n equals 123. Just as before, we start by converting the number to a string, resulting in digits equals 123. Next, we calculate the total number of digits, which is the length of the string. Since there are 3 digits, power equals 3. Now we compute the sum of each digit raised to the power of 3 using a generator expression. For the first digit, 1, we calculate 1 3 equals 1. For the second digit, 2, we calculate 2 3 equals 8. For the third digit, 3, we calculate 3 3 equals 27. Adding these values together gives us Armstrong_sum equals 1 plus 8 plus 27, which equals 36. Finally, we compare this sum to the original number. Since Armstrong_sum equals n, or 36 equals 123, is false, we conclude that 123 is not an Armstrong number. Therefore, the final output for this example is false. The time complexity of the is_Armstrong function can be broken down into individual steps. First, when we convert the number n into its string representation using str n, the time required is proportional to the number of digits in n, which we denote as d. This step takes d time because each digit must be processed during the conversion. Next, calculating the number of digits using len digits is an O1 operation in Python. This is because the length of a string is stored as metadata and does not require iterating through the string. Lastly, we compute the sum of powers using a generator expression. This involves iterating through each digit, converting it to an integer in O1 time per digit, and raising it to the power of d. Python's efficient algorithms for exponentiation mean that raising a number to a power d takes O log d in time. Thus, for d digits, the total time required for this step is O d asterisk log d. These steps together form the basis for analyzing the function's overall time complexity. Now, combining all the steps, the dominant term is the computation of the sum of powers, which takes O d asterisk log d time. Comparing the computed sum with the original number, Armstrong_sum equals n, is an O1 operation. Therefore, the overall time complexity of the function is O d asterisk log d, where d is the number of digits in n. Since the number of digits d is related to the magnitude of n as d equals log 10 n, we can also express the time complexity as O log n asterisk log n. Moving on to space complexity, the function's memory usage depends on the storage requirements. Converting n to its string representation requires O d space because the string must store all d digits. Additionally, the generator expression used for summing the powers does not create a full list in memory. Instead, it generates each value on the fly, making its space usage O1. In addition to the string representation, the function uses a constant amount of memory for variables such as power, Armstrong_sum, and intermediate calculations. When we combine all these factors, the overall space complexity of the function is O, d, where d is the number of digits in n. To put this into perspective, a brute force approach would involve iterating through all numbers up to n and checking each one individually. This would result in a time complexity of O, n d log, d, which is far less efficient than the current solution. The optimized approach directly computes whether a specific number is an Armstrong number by focusing only on the necessary calculations, avoiding redundant work and leveraging Python's efficient handling of exponentiation. Now, let's consider the best, worst, and average case analysis. For this function, the time complexity remains consistent regardless of the input value of n. The function performs the same sequence of operations for any given n, so the best, worst, and average case complexities are all O, d log, d. In conclusion, the function is efficient for verifying a single Armstrong number. Its time complexity, dominated by the sum of powers calculation, is O, d log, d, or equivalently O, log, n, log, n. The space complexity is O, d, stemming from the string representation of n. This approach is optimal for this problem, as it directly aligns with the mathematical definition of an Armstrong number while minimizing computational and memory overhead. One common area where mistakes arise in solving Armstrong number problems is misunderstanding the role of the number of digits. Each digit in the number must be raised to the power of the total number of digits in that number. If you hardcode a fixed power, like raising all digits to the third power, it will only work for numbers with exactly 3 digits, leading to incorrect results for numbers of other lengths. Another frequent mistake occurs when splitting digits. This usually involves integer division and modulo operations, but if these are not implemented correctly, especially for numbers with varying lengths, it can lead to errors or even infinite loops. Precision errors are another challenge, particularly when exponentiation is performed in a language that relies on floating-point arithmetic. Armstrong number checks require exact equality, and even a tiny precision mismatch can cause the algorithm to fail. Always ensure your implementation handles these cases properly to avoid incorrect results. Inefficiency is another common pitfall when implementing solutions to Armstrong number problems. A brute force approach, which tests every number up to a large limit, is often wasteful because Armstrong numbers for an n-digit number must fall within a specific range. For example, numbers with 3 digits will only produce Armstrong numbers between 1 raised to the third power and 9 raised to the third power, multiplied by 3. Testing numbers outside this range is unnecessary and adds computational overhead. Another area to watch for is edge cases. Single-digit numbers, for instance, are all Armstrong numbers by definition, but they are sometimes overlooked. Similarly, failing to account for large numbers with many digits can lead to incomplete testing. It's critical to handle these edge cases carefully to ensure your solution is robust and accurate. Understanding the mathematical properties of Armstrong numbers can provide valuable insights during interviews. Armstrong numbers are rare, and their occurrence depends heavily on the number of digits in the number. By leveraging this knowledge, you can optimize your solution by pre-computing the range of possible Armstrong numbers for a given digit count. For instance, a 3-digit Armstrong number will always lie between 100 and 999. This eliminates unnecessary computations. Another useful optimization is to extract digits using a list or string instead of modulo and division operations. This approach not only simplifies the logic but also improves code readability. Be prepared to explain the mathematical reasoning behind Armstrong numbers if asked. This includes discussing why the range is limited based on the number of digits. Additionally, you might encounter variations of the problem, such as finding Armstrong numbers within a specific range, verifying if a given number is an Armstrong number, or generalizing the concept to higher powers or custom rules. Preparing for these variations will help you tackle similar challenges effectively. Armstrong number problems share similarities with other number-based problems on platforms like LeetCode. For example, in LeetCode 9, the palindrome number problem, you use similar digit manipulation techniques to determine if a number reads the same forward and backward. In LeetCode 202, the happy number problem, you sum the squares of digits and check for cycles, which involves a similar iterative process. LeetCode 263, the ugly number problem, focuses on mathematical properties of numbers, while LeetCode 412, the fizz-buzz problem, emphasizes clean, efficient implementations for solving number-related conditions. Exploring these related problems can help you refine your approach to Armstrong numbers, as the core ideas of digit manipulation, mathematical properties, and efficient implementation are shared across these challenges. When solving Armstrong number problems, there are several approaches you can consider. The brute force method involves iterating through all numbers in a given range, calculating the sum of the digits raised to the power of their count, and checking if the result matches the original number. While simple to implement, this approach becomes inefficient for large ranges. An alternative is pre-computation and lookup. Here, you pre-compute all Armstrong numbers within specific ranges, like 1-digit, 2-digit, or 3-digit numbers, and store them in a list. During execution, you simply check if a number is in the pre-computed list. This is much faster but requires additional storage. Another approach is to narrow the search space using mathematical range limitations. By understanding that an n-digit Armstrong number cannot exceed 9 raised to the nth power, multiplied by n, you can significantly reduce the numbers you need to test. This trade-off reduces computation but requires careful calculation of the range boundaries. Each of these methods has its strengths, so choose the one that best suits the problem constraints and requirements. Great job! To wrap up, we've learned how to identify Armstrong numbers by summing the powers of their digits and comparing the result to the original number. This problem teaches us about digit manipulation and mathematical patterns. Thanks for watching, and stay tuned for more exciting challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!